like to recall in case of a DC motor. Can you tell me what happens if we use, instead of the split ring or the commutator segments in a DC motor, only slip rings are used? What happens to the motor operation? Can anybody answer? This we have discussed earlier, but still I want you to recall. Hello? You got the question? I'm audible to you?
Yes, sir.
How a DC motor behaves when we use slip rings instead of split rings or commutator segments. Chandramohan? Hello? Vaibhav, Bharati, Sukrut, others? Is my question clear?
So the motor will not run, sir.
Will not run means what? There are several meanings for will not run.
I mean to say,
we are not technical people and we must be very clear about it.
sir, I mean to say that the motor will not rotate in anti-clockwise direction, sir, continuously.
Exactly. Good, correct. The motor will not rotate in one direction continuously. Otherwise, unidirectional torque is not established. For the motor to run in one direction continuously, and unidirectional torque has to establish. That is not possible if we do not have the commutator segments and have only slip rings. And therefore, in the absence of the commutator segment or the split ring, the motor becomes what we call non-self-starting. Are you getting this? The motor becomes non-self-starting. That means it cannot start. And to make it start, the only way is to replace slip rings by split rings. Therefore, we call for a DC motor split ring as a starter. Are you able to follow this?
Yes, sir.
And a very similar situation we come across in case of synchronous motor. And we will see what is that and how the synchronous motor takes its name synchronous. And this is what the article aims at. And can you see this diagram?
Yes, sir.
Towards the left, again, please note, a synchronous motor similar to a synchronous generator or alternator has two parts, namely stator and rotor. The difference between the two machines is that in an alternator, we supply mechanical power to the rotor and make it to rotate or run. And in the process, we take out electrical power from the stator. Is it right?
Yes.
Whereas in a synchronous motor, again, the parts remain the same, the stator and rotor, but the power flow gets reversed in the sense that we give electrical power input to the stator. That is what shown in the diagram on the left. And we take the power output from the rotor, okay, Of course, that is not shown here. The rotor is shown on the right, but we have shown a DC supply for the rotor. Of course, in alternators also we do that. The rotor is supplied with a DC electrical power to establish magnetic flux. In the same way here also, in addition to that, here the rotor develops a torque, and that torque will make the rotor to rotate, and hence the rotor carries mechanical power output. Are you able to understand this?
Yes, sir.
Right. And further, we also discussed in case of alternator that there are basically two types of fluxes, magnetic fluxes available in the machine. Can you name them? What are the two types of fluxes?
So main flux and armature flux.
Exactly. Main flux and armature flux. Armature flux has one more name. What is that?
Rotor flux.
No, no. Armature is not rotor. What is armature in an alternator?
Stator, sir.
Stator. Correct. Armature doesn't rotate in an alternator. Even in case of a synchronous motor also, it will not rotate. Therefore, in a synchronous machine, in general, the meaning of armature is stator. So we have stator flux, that is armature flux, and main field flux. Correct? Similarly, in this synchronous motor also we have two fluxes, stator flux and rotor flux. That is what the diagram shows. The one on the left, what we understand is a three-phase supply is given to the stator, and on the right, a DC supply is given to the rotor. Are you able to visualize this?
Yes, sir.
Now, I will just go through these lines slowly. Stator and rotor are the two main parts of synchronous motor. The stator is the stationary part, and rotor is rotating part. The stator is excited by three-phase supply, and rotor is excited by DC supply. Correct?
Yes, sir.
Right. The term excitation means magnetic field induced in the stator and rotor of the machine. The main aim of the excitation is to convert stator and rotor into electromagnet. So why you have to excite the stator and rotor in case of synchronous motor is to make them act as electromagnets. Is it clear?
Yes, sir.
Right. The three-phase supply, which is given to the stator, that is on the left we have shown here in the diagram, induces north and south pole on the stator. That means it makes stator to act as electromagnet. The three-phase supply is sinusoidal. The polarity, positive and negative of the wave changes after every half cycle. Because of this, the north and south pole also keeps changing. Are you able to understand this?
Yes, sir.
That means when the stator is applied with a three-phase voltage, the three-phase voltage being a sinusoidal voltage will make the poles on the stator also to vary at regular intervals. When this goes positive, that becomes a north pole. When this goes negative, it becomes south pole, and it keeps changing. Therefore, the scenario as far as the stator is concerned, on applying a three-phase voltage, the magnetic poles are induced in the stator, and these poles will keep changing their polarity at regular interval of time. Is it okay? Hello?
Yes, sir.
Yeah. And since the poles are getting their polarity changed at regular interval, that results in what we call a rotating magnetic field. I think I had asked you to go through this article somewhere earlier. Can you remember? A three-phase voltage applied to an armature or conductor or winding will result in rotating magnetic field. I had asked you to go through this article. Remember that? Hello? Chandramohan? Hello? Bharati? Vaibhav?
Sir, nothing like that have you told, sir.
ಹೇಳಿದ್ದೀನಪ್ಪ ಜ್ಞಾಪಿಸ್ಕೊಳ್ಳಿ. Chandramohan, can you remember that? Other students? Hello? Bharati? Had I told this earlier? Okay, doesn't matter. So I want you to go through this article, how three-phase voltage will result in rotating magnetic field. Matter of fact, a very brief answer to that is what we discussed just now. Three-phase supply is sinusoidal and its polarity keeps changing at regular interval of time. That being the case, when such a voltage is applied to the stator or the armature, that results in magnetic poles which vary in polarity at regular interval of time. And this means that the magnetic field which is so induced will be rotating in nature. Is it clear? Now at this point, you just remember this and you can go through this article leisurely after some time. When I apply three-phase voltage to armature, it results in rotating magnetic field. And that is what we have in the stator. Is it clear now?
Yes, sir.
Yes, sir.
But the magnetic field which develops on the rotor, it is not rotating because rotor initially is not rotating. I repeat, in case of synchronous motor, rotor initially is not rotating. And therefore, when I apply a DC supply to a non-rotating winding, it will not result in a rotating magnetic field. It will result only in a static magnetic field. ಗೊತ್ತಾಯ್ತಾ ಇದು?
Yes, sir.
The polarity of the DC supply on the rotor becomes fixed, and thus the stationary magnetic field develops on the rotor. What this means is the north and south pole developed on the rotor will be fixed. They don't change at regular interval of time. ಗೊತ್ತಾಗ್ತಿದ್ಯಾ?
Yes, sir.
So,
Yes, sir.
can you tell me now? Yeah, please, Rama.
Nothing, sir.
Okay. So we have two magnetic fields, one on the stator, one on the rotor. The difference is that the magnetic field on the stator is changing in polarity and hence it rotates at constant speed. Whereas the magnetic field developed on the rotor is by a DC supply, therefore, and further, initially the rotor is not rotating, therefore, that magnetic field on the rotor will not be rotating, which means that the south and north pole positions are fixed. Is it fine?
Yes, sir.
Yes, sir.
The speed at which the rotating magnetic field, that is stator magnetic field, uh, rotates is known as synchronous speed. So what we understand is the stator magnetic field is a rotating one, and the speed at which it rotates is called synchronous speed. And that synchronous speed is nothing but 120 F by P. That means it depends on what frequency of the supply voltage prevails and number of poles on the stator. So depending on that, the speed of the rotating magnetic field is fixed. Is it clear?
Yes, sir.
Yes, sir.
Okay. Now, let us see how these two fields interact and what happens to the motor. When the opposite pole of the stator and rotor face each other, that means the stator, let us assume that stator north pole and rotor south pole, they face each other. Let us assume. Then force of attraction occurs between them. The attraction force develops the torque in the anti-clockwise direction. The torque is a kind of force which moves the object in the rotation. Thus, the poles of the rotor drag towards the poles of the stator. So that means when the two poles, the rotor pole and the stator pole, are having opposite polarity, then the motor will certainly rotate anti-clockwise because of the dragging force between the two poles. Is it clear? After every half cycle, the pole on the stator is reversed. You see, if the pole on the stator is also static, that means its polarity will not change, similar to the rotor, then this kind of attractive force will be continuously present, and that makes the torque also unidirectional, and hence the motor would rotate in one direction constantly. But that is not the case in case of synchronous motor, because in synchronous motor, the field in the stator is alternating in polarity. Therefore, one time the pole on the stator and the pole on the rotor, they face each other with opposite polarity. The other time with the same polarity. And we will see how it happens. After every half cycle, the pole on the stator is reversed. The position of the rotor remains the same because of the inertia. So what's happening is, you see, like that is shown in the figure 1. Can you see this figure?
Yes, sir.
Yes, sir.
And here, for the explanation purpose, we have considered rotor to have two poles, south top, north bottom. Okay. And further, at some position of the stator magnetic field, the magnetic field of the stator has its north pole on the top and south pole on the bottom. And hence, in this position, the two poles are attracting. You see, south of the rotor, north of the stator, they attract. And similarly, north of the rotor and south of the stator, they attract. And this will certainly create a torque which will try to rotate in anti-clockwise direction. Are you able to understand this?
Sir, could you
Yes, sir.
explain that torque production once more, sir?
Sure. You see, what we understand is there are two magnetic fields. One the stator, other one the rotor. The stator magnetic field is rotating continuously at a constant speed called synchronous speed, given by 120 F by P. Whereas a rotor magnetic field is static field. Correct? This point is clear?
Yes, sir.
Now, for the purpose of understanding, we have taken a two-pole machine. That means the rotor has two poles, south and north as shown. And please note, this position is fixed because right now, initially, the rotor is not rotating. Are you understanding this point?
Yes, sir.
So since the rotor is not rotating at this point of time, initially, the south pole and north pole positions are fixed. But the stator poles are changing their polarities at regular interval of time because they are being created by a three-phase supply which is alternating in nature. And therefore, these poles will change the polarity at regular interval of time. Now, we have considered one particular instant of time wherein the north pole of the stator and the south pole of the stator face each other as shown in the figure. Are you able to understand this?
Yes, sir. Yes, sir.
If in that case, what happens is an attractive force gets developed, which in turn will constitute a torque, which will try to rotate anti-clockwise in this way. Agreed?
Agreed, sir.
Right. Now, what happens is the rotor, though it is now being moved by the torque, but still the pace at which or the speed at which the rotor rotates will be very, very less compared to the speed at which the stator magnetic field rotates. Are you able to follow this?
Yes, sir.
And because of the inertia, the rotation of the rotor will be very, very slow initially. It has to overcome the inertia. So, which means effectively we can say that the south and north pole of the rotor, the position of these poles will not change initially for a small time, will not change. Whereas the position of the poles on the stator will change because it is rotating at a very high speed. बताते
Yes, sir.
Okay. So that is the concept behind. Now we will see, that being the case, what happens in the subsequent time. So you see, in figure 2, what we see is the rotor poles are, being fixed in position. They remain the same as before, that is as in figure 1, but the stator pole have changed their polarity. Earlier, the top one was north and the bottom one was in south, but now it is interchanged. The top one has become south, bottom one has become north. Are you able to note this difference?
Yes, sir.
And hence, we understand that the two poles are being like poles, they repel. So repel means a torque in the opposite direction gets developed. Otherwise, that torque will try to pull the rotor clockwise. ಗೊತ್ತಾಗ್ತಿದೆಯಪ್ಪ?
Yes, sir.
And hence, this keeps going, and we see that only pulsating torque gets developed in the motor, which will not be, which cannot rotate the rotor in one particular direction, and hence we say that synchronous motor is a non-self-starting motor. Is it clear?
Yes, sir.
So why synchronous motor is not self-starting? Anyone? Chandramohan, can you try why it is non-self-starting?
Sir, because the pulsating torque changes the direction of rotors.
Yeah, because the torque produced being pulsating in nature cannot drive the rotor in one particular direction. And hence we say that synchronous motor is non-self-starting. So, which means that we require some starting mechanism for the motor. And I told earlier that in a DC motor, that starting mechanism is a commutator. Agreed?
Yes, sir.
And similarly, in this case, we require some starting mechanism. So what is that? That means we have to somehow see that the rotor is rotated physically. ಗೊತ್ತಾಗ್ತಿದೆಯಾ?
Yes, sir.
I don't know whether you are aware of this. Like earlier, in the old vehicles, cars and lorries, okay, there was no self-starting mechanism. So we have to use some external power, external physical power to rotate the engine and make it start. So in the same way here, we have to do some physical means to rotate the rotor, because the rotor is not rotatable on its own because of this pulsating torque. ಗೊತ್ತಾಗ್ತಿದೆಯಾ?
Yes, sir.
Okay. Now, the method or the mechanism which we adopt to rotate the rotor and hence see that the pulsating torque is eliminated or a continuous torque is established, that is called starter for synchronous motor. So what's the starter? What's a starter for induction? For synchronous motor?
The starter is used to reduce pulsating torque and to produce a continuous torque, sir.
Correct. Okay. So that means we we have to physically rotate the rotor. And you see, once the rotor also starts rotating along with the stator magnetic field, which is also rotating, okay, then there is no question of the two poles facing each other in the same polarity. ಗೊತ್ತಾಗ್ತಿದ್ಯಾ? Is it clear?
So can you tell once again, sir?
Yeah. You see, why this pulsating torque concept has come here? Only the stator magnetic field is rotating continuously at a higher speed, and the rotor is not able to rotate at that speed. And that being the case, at some instant, the poles will face each other like poles, and some other instant, the poles which face each other, they become unlike poles. That results in a pulsating torque. Now, to overcome this problem and make the torque unidirectional, we also rotate the rotor by some external means. When we do this, what happens is both the fields are now rotating. And there is no way a pulsating torque gets established because both are rotating, and hence at any point of time, the poles will be unlike poles only facing each other. That makes the torque unidirectional and the rotor starts rotating. Is it clear?
Yes, sir.
And once the rotor starts rotating, it will rotate at synchronous speed only. Why? Because this rotor is being dragged or pulled by the synchronous field created in the stator. Otherwise, the stator field will lock the rotor field and it will just drag it at its own pace. Otherwise, if I go one step further, what it means is once the interlock takes place between the two fields, the rotor will run at synchronous speed only. At no other speed it will run. ಗೊತ್ತಾಗ್ತಿದ್ಯಾ?
Yes, sir.
Hence, the induction motor runs only at synchronous speed and therefore it takes the name synchronous motor. Is it clear?
Yes, sir.
The speed of the motor is fixed and the motor continuously rotates at synchronous speed. Hence, the motor is named as synchronous motor. Any doubt here? So this is the operating principle of synchronous motor, why it becomes pulsating initially, and what is required to make it unidirectional, and why it is called synchronous motor. Any doubt? I can answer.
Sir, I just want one clarification, sir.
Help me.
Sir, you just said that the starting mechanism part for the synchronous motor would be like a rotor would be rotated physically, no, sir, by external means.
Howdo.
Like, how do we know that, sir, that the rotor and the stator field would be rotating in the same direction, sir? Like, how do we identify the direction?
Yeah, that's a very good question. Yes, that you have to initially confirm, and that we will see when we discuss the methods to start. Okay.
Okay, sir. Sir, what if they're running in the opposite, sir? Like, will the pulsating thing increase, sir?
Yes, obviously.
Okay.
They cannot go in opposite direction.
Okay, sir. Okay.
And that we have to confirm before doing anything with the starting mechanism.
Okay,
Yeah, that's
sir.
true. Your question is valid. Okay.
Yes, sir. Clarified, sir.
Right. Now let us take up the second article. Second article is how the synchronous motor operates or behaves under constant load and variable excitation. Like we know, for a machine, as the load increases, the input power also increases. For example, if it is alternator, the load is electrical. As electrical energy output is increased, the mechanical input is also increased. That we have seen, and that is the concept leading to load angle. Can you recall this? Or power angle, delta.
Yes, sir.
In the same way, for a synchronous motor also, the load being mechanical, correct? As the mechanical load increases, the electrical input also increases. And we know electrical input, when I say electrical input in terms of load variation, it is current. Agreed?
Yes, sir.
Yes, sir.
So as the load on the synchronous motor increases, the current taken from the mains or the stator current also increases. That is simple. But here in this article, we are trying to understand the other aspect of it. That means under a constant load, that means the load is not changed. The load is same. When the load is same, the power input is also same. I repeat, when the load is same, power input is same. Agreed?
Yes, sir.
Yes, sir.
But excitation is variable. Excitation ಅಂದ್ರೆ ಯಾವುದು? DC excitation. for the rotor.
Yes, sir.
So this article talks about the behavior of a synchronous motor under constant load, which means the input power being constant and excitation being varied. And here we see 4 phasor diagrams. Kanta idea? Is it okay? Kanta idea?
Yes,
Yes,
sir.
sir.
Yes, sir. It's visible.
Right. Now, the first diagram is for normal excitation. Again, please note, in case of alternator, when I say EB or EPH, it is induced EMF. Correct?
Yes, sir.
VPH ಅಂತ ಹೇಳಿದ್ರೆ alternator ಕೇಸಲ್ಲಿ it is output voltage. Agreed?
Yes, sir.
But ಇಲ್ಲಿ in case of synchronous motor ಉಲ್ಟಾ, VPH ಅಂದ್ರೆ it is applied voltage to the stator. ಸರಿನಾ?
Yes, sir.
EPH ಅಂದ್ರೆ it is induced voltage in the stator. Induced voltage ಅಂದ್ರೆ ಏನರ್ಥ ಇಲ್ಲಿ? When the rotor starts rotating, obviously the synchronous motor operates as an alternator. ಹೌದಾನೆ?
Yes, sir.
So when we apply a 3-phase voltage to stator, that will make the rotor to rotate, and when the rotor rotates, EMF is induced in the stator. Very similar to the concept of back EMF in a DC motor, if you can recall. Okay, na?
Yes, sir.
So illi VPH is applied voltage, and we have taken a lagging power factor. Okay, so IA, that is the input current in the stator, lags the applied voltage by 5. Then we have the induced EMF shown as EBPH here. And the situation is normal excitation means both EBPH and VPH are equal in magnitude. ಗೊತ್ತಾಗ್ತಿದೆಯಾ?
Yes, sir.
That means I'm going to adjust the field excitation in such a way that the induced EMF will be equal to applied voltage. We call such an excitation as normal excitation. In that case, what we understand is, you see, the phasor diagram is as shown, and this is delta, power angle or the load angle. Okay, and the angle between resultant of these two voltages is ER, that and the current is angle theta. It's okay?
Yes, sir.
Now we will see what happens in this condition. Consider normal behavior of the synchronous motor where excitation is adjusted to get EB equal to V. That's called normal excitation. Under this condition, motor is drawing certain current from the supply and power input to the motor is P in. So here what we are trying to understand is the motor is loaded with a constant load and excitation is normal, which makes EMF induced equal to applied voltage. Then the power taken by the motor will be P in. And the power factor is as shown, which is a lagging power factor. Now, when the excitation is changed, there is hardly any change in the losses of the motor because loss will not depend on the excitation. I repeat, loss will not depend on excitation. So the power input also remains same for constant load, demanding the same power output. That means as long as you keep the load constant, the power output will also remain constant. ಗೊತ್ತಾಗ್ತಿದೆ ಇದು?
Yes, sir.
Now, power input is 3 times VPH IPH cos phi, where phi is the angle between the applied voltage and the armature current or the stator current. It's okay?
Yes, sir.
Most of the time, voltage applied to the motor is constant. Therefore, constant power input means IPH cos phi remains constant. Is this point clear? When I say power input is constant for a constant voltage, it means that IPH cos phi is constant. Correct?
Yes, sir.
Therefore, so motor adjusts its cos phi, that is power factor, and so that Ia cos phi remains constant when excitation of the motor is changed, keeping load constant. So that means when we are keeping the load constant and trying to vary the excitation, what happens is the power factor keeps changing in order to keep Ia cos phi constant. ಗೊತ್ತಾಗ್ತಿದೆಯಾ?
Yes, sir.
ಅಂದ್ರೆ ಏನರ್ಥ ಅಂದ್ರೆ when we change excitation, you see, I will go to this. I'm referring to second figure B, which we call under excitation. ಅಂದ್ರೆ ಇಲ್ಲಿ ಏನಾಗಿರುತ್ತೆ ಅಂದ್ರೆ EBPH will be less than VPH, and hence the resultant EMF will be different from the KCA. ಗೊತ್ತಾಗ್ತಿದೆಯಾ ಇಲ್ಲಿ? Can you compare these two figures?
Yes.
Hello. When you change the excitation, when induced EMF goes less than applied voltage, then the resultant EMF also changes. Since the resultant EMF changes, the stator current also changes because stator current depends on resultant EMF. ಗೊತ್ತಾಗ್ತಿದೆಯಾ?
Yes, sir.
And since stator current changes, in order to keep stator current into cos phi constant, because the load is constant, cos phi will also change. ಗೊತ್ತಾಗ್ತಿದೆಯಾ?
Yes, sir.
So that means when you make the excitation to change, the power factor will automatically change to keep the power constant. So the figure B will tell us that the power factor becomes more and more lagging as we make the excitation under excited, and in which case the armature current keeps increasing, and the angle between armature current and the applied voltage also increases. Otherwise, it becomes more lagging. ಗೊತ್ತಾಗ್ತಿದೆಯಪ್ಪ?
Yes, sir.
And similarly, in the third figure, the diagram C, over excitation. That means I make the field excitation in such a way that E becomes greater than VPH, in which case the phasor diagram is as shown. So here we see the current gets shifted above the applied voltage because now it becomes leading, and the resultant EMF is here. And again, the power factor will change to maintain the power constant. But this time, the power factor becomes leading power factor. Therefore, we say that a synchronous motor, when it is overexcited, works as a leading power factor machine. Is it good or bad? Hello? If
Bad,
any
sir.
electric, think and tell me. If any electrical system works as a leading PF system, is it good or bad? Vaibhav? Sukrut is not there? Chandramohan,
Sir.
can you think? Hello, Vaibhav. Helapa.
Maybe bad, sir.
No. Electrical engineers, ಇದು ತುಂಬಾ ಮುಖ್ಯ ಇದು. We want more and more leading power factor systems. ಏನಕ್ಕೆ ಅಂದ್ರೆ, I think I have told this earlier, majority of the loads what we have, the electrical systems what we have, they are lagging. And all these lagging loads, they result in increased kVAR, reactive power component. Any increased power, reactive power component is bad. ಗೊತ್ತಾಗ್ತಿದ್ಯಾ?
Yes, sir.
Therefore, since we have majority of the loads being lagging in nature, if some load like synchronous motor is a load for us. ಹೌದಾ ಇಲ್ವೋ?
Yes, sir.
Because it is consuming electrical energy. So, if this operates as a leading power factor load, that is excellent because it will compensate for the lagging power factor loads. And hence, it will make the overall power factor better. ಗೊತ್ತಾಗ್ತಿದ್ಯಾ?
Yes, sir.
And that is what we do, power factor correction ಅಂತಾನೆ ಮಾಡ್ತೀವಿ. And for that purpose, we use capacitor. Don't you know this? Hello? We
Sir,
use
no, sir.
capacitors to improve power factor. You know this or not?
Sir,
No,
no,
sir.
sir.
Yeah, you must know. Capacitors are used invariably to improve power factor in electrical networks. So that job is being done by a synchronous motor. And hence, synchronous motor is also called a synchronous condenser because there is another name for capacitor, that is condenser. ಗೊತ್ತಾಗ್ತಿದ್ಯಾ?
Yes, sir.
And there is last figure talks about critical excitation, wherein the magnitude wise EMF induced and applied voltage are same, but the excitation is such that it will result in a unity power factor. That means the current and voltage will be on the same line. ನೋಡಿ ಇಲ್ಲಿ ಗೊತ್ತಾಗ್ತಿದ್ಯಾ?
Yes, sir.
And when the power factor becomes unity, can you tell me what should happen to the current for the same power input? ಕಮ್ಮಿ ಆಗುತ್ತಾ ಜಾಸ್ತಿ ಆಗುತ್ತಾ ಕರೆಂಟು?
So remains constant, sir.
ಹೇಗೋ? I repeat, you see, IA cos phi should remain constant because my load is constant. All these discussions are under constant load. Therefore, IA cos phi should remain constant because my voltage is constant. And therefore, as cos phi becomes 1, which is the maximum value for cos phi, what should become, what should happen to IA? Vaibhav?
Should decrease, sir, or reduce.
Yes, that will become minimum. And that is the concept of V and inverted V curves, which we are going to discuss in future. Is it clear? So we will stop here. Any doubt? And here in a table, we have shown how the motor behaves for different excitation. Under excitation, it is lagging. Over excitation, it is leading. Critical excitation, it is unity power factor. Normal excitation, also it is lagging. Okay, we'll stop here. And we will meet the next class.